All right, thanks, Frank. Appreciate the time today to talk about sort of what we're doing at Elastics.cloud and how we're trying to think differently about the benefits of CXL and how we can use CXL to accomplish many of the system level kinds of functionality as well as performance. So a little bit about our company. We started about 2 years ago. Myself and co-founder Shreyas Shah. Our genesis comes from the work we did at PLX Technology. So at PLX, we designed the Gen 1, Gen 2, Gen 3 PCI Express bridges and then switches. All right. PLX was acquired by Avago, which became Broadcom, and the architectures that we created back at PLX with PCI Express are the products that you see today in the market from Broadcom on PCI Express. So with that was a lot of learning came with the work that we did there. And as we started looking at next generation I/O technology, we were looking at many of the I/O buses that were being proposed throughout the years. And it became evident that CXL would basically be the winner. And so since then, we've been looking at how can we take what we learned, the positive things about PCI Express and the negative things about PCI Express, and try to put them together as part of the CXL solution so that we could get better performance, right? One of the things that we looked at was SRIOV, as everyone who's been involved in PCI Express knows. And one can say that was mildly successful. Many things now support SRIOV, and kind of NVMe kind of came a little bit from that. But MRIOV was another thing that we attempted to do that was very, very difficult. And it was difficult because of the PCI Express, the nature of PCI Express and its point-to-point paradigm, I guess, right, with how it connected to the processors. And so when we got together, we tried to look at, okay, how can we enable better functionality using CXL and the way the CXL is being defined. So today I'll talk a little bit about sort of some of the aspects that we're putting into our device and how we expect those will be able to improve overall performance at the system level. So to date, we've got 60 engineers worldwide. We are actively working on our designs. We have things running in FPGA today, and we'll talk a little bit about where we're going there. So the problem that we're trying to solve, I think, is one, as I said before, we're looking at things from a system level perspective, right? Exponentially increasing data, right? The need to monetize that data and to be able to control the costs associated with that. But the other thing that we saw appearing over the years is what we called a tiered data center model, right? Where we've got things that are obviously large enough and extremely large that they need to be done in the cloud. But now with 5G coming on board, there's some processing now that's going to have to be done at sort of those 5G aggregation points or central offices. And then with the amount of data that's being generated out on the edge, there's processing that has to be done there as well, because all of that data can't be shipped into the core of the network. The speed of light is not fast enough, the wires aren't wide enough, and it's very costly in order to do that. So what we find is there's a lot of companies that are now starting to curate that data, right? So they can do some of the near-term processing, the time-sensitive kinds of processing out on the edge, and then maybe extract the relevant data that then goes into the core of the network for the large training and things that need to be done on the AI/ML standpoint. So the name Elastics.cloud comes from our perception, right, that we're going to have to be able to process this data all along that spectrum of this tiered data center model, right, and to have the elasticity in terms of how we do that processing and how we connect these devices together in order to enable that tiered data center model to appear and to be effective, right? And so then we start looking at the interconnect, and we realize that in order to get this kind of system performance, that it's more than just the interconnect, right? How we connect these devices is one aspect of it, But then how do you use it at the system level? How do you use it to create the architectures or the specific architectures that are required for some of these workloads? And how do you remove the bottlenecks that were created by PCI Express because of its point-to-point protocol nature, right? And then with that, how do you enable this heterogeneous compute environment that we're starting to see, right? Because you need more and more specialized processors that get put into play, and then combine that with all of the other components that are necessary from compute, memory, storage, networking. It becomes a significant problem in terms of not just the connectivity, but the management of those devices as you start to create these kinds of topologies. And then, as you've heard everywhere in the last couple of days and various shows, memory is now at the forefront of all this. And it is that because the cost of memory, right, is now exceeding the cost of even compute, right, in the data center. So how do we get better use of that? How do we use that more effectively? And then how do you get the performance out of that and eliminate the excessive copying of data into and out of processor memory in order to get some of these tasks completed? So these are the things that we looked at and the things that we're trying to solve and that we are solving today as part of our products. So, for us, it's the 4 Cs, right? Control, cost, composability, and connectivity, right? On the control side, now that we've got these devices that can be connected together, how are we controlling them and how are we managing them, right? If we connect these thousands of devices together, but yet they're still controlled by a single processor, now we've created an even bigger bottleneck through that processor, right? So for us, it's having to be able to add that ability of distributed control of these resources and to be able to then create workload-centric architectures as opposed to server-centric architectures that will allow us to alleviate some of those bottlenecks that we see today in the data center, right? In a dual socket server in the data center, one of those sockets is used primarily just to manipulate and move data around, right? It's expensive to do that, right? And it leads to overall lower utilization of those components, right? On the cost-saving side, right, eliminate stranded resources, right, to be able to have better effective utilization of those and to be able to take those resources and compose them in such a way that they're right-sized, fit to the workloads that need to be executed, right? And then finally the connectivity to be able to have the scale out that's required for some of these systems to, as the previous presentation talked about, in the thousands of devices that get connected. So here's an example, it's just round numbers that we've put together on the memory problem, right? If you look at a 40 rack server, we can argue that 1/3 of that memory in that server is used for the near CPU task, direct attached DRAM functions that are required, right? But another 1/3 of that memory is memory that can be shared and be pooled, right? And so to be able to enable that, it could add additional savings, right? And then 25% of that memory is stranded that never gets used. So if we just address the stranded memory, right, and we add shared memory, right, we eliminate that stranded memory, we put it with CXL, right, we're calculating that it's probably on a rack level basis, right, about $200,000 of savings, right, based on 40 servers in a rack. Right? And then you multiply that by the number of racks that are sold each year, it's about 400K. You're talking an $80 billion problem, right? This is why everybody is so interested in how do we save memory, right? And that's just in the component costs. But then you add to that the better utilization, the increased capacity, the ability to run more workloads through because now you've eliminated some of these bottlenecks, right? Now your overall performance goes up significantly. Right? And I'll show you some real data on that. And that, again, contributes to the overall lower TCO. So what we're looking at is performance at a price point, right? And optimizing that, right? And by doing that, that makes us valuable from a company standpoint. But this is the sort of framing the $80 billion problem, as we call it internally. So what we've started, and now with the functionality that we have currently in FPGA, This is something that we have running in the lab today, and I encourage anybody who wants to come and visit our lab and talk about the things and actually see and touch and feel what we're doing. Please get in contact with me or through our website, and we're glad to demonstrate this to you. But in this example, we've got two servers, server A and server B, right? Each of those servers have a processor in that, and that processor has direct attached memory. Right? In addition, we have an FPGA card that we can plug into the CXL slot in that server, and there is memory on that FPGA card. Right? So we have that in server A and server B, and then we can connect server A FPGA card to server B FPGA card through a cable. Right? And so now we have the ability for CPU A to contact or work with memory that's in FPGA-B. So the blue part of the memory on one side and the green part of memory on the other side sort of working together and being able to access memory on each server, right? We can run this concurrently, right? And the ability for the various processors to work at the same time, be able to access this memory, right? In the next show that we're going to attend, Supercomputing 22, we will actually show on the floor our ability to do this with multiple servers. And if I can get as many servers as I can, I will put as many of those on the floor, because this solution is extendable to multiple servers and also multiple appliances. So it doesn't have to be a server that we connect to. It could be a memory appliance that's connected to multiple servers that we're talking to. And this is up and running today in the lab. And so one of the things I asked the team to do, I said, okay, now that we've got this working, what does this mean, right? And what does this mean in terms of performance? And so we had one of our employees go and implement a Redis Labs database onto our server. And what we did was we had the database be large enough so that the data would have to swap, right? Which we see typically in these very, very large databases. Today, it swaps to SSD, right? And so that was one experiment, is okay, let's take measurements on what happens when this large database and we run operations and latency and bandwidth, right, when it's swapping to SSD. And on the other hand, we swap to memory that's located on the FPGA card that's plugged into the system. So instead of swapping to SSD, we swap to the FPGA card through CXL attached memory. Right? And what we see is, even in that instance where the FPGA card is still, relatively high level of latency, it's still orders of magnitude, right, better than what we see swapping to SSD. So even by growing that memory space in an FPGA card, we're seeing 20x better latency, right? We're seeing 20x better operations per second and significantly more bandwidth. Right? And as the data sets increase in size, this becomes even more and more relevant. Right? So this we have running today, and it exemplifies what we can do with CXL and what we can do with the ability to share these memories, right? From a system level perspective. So we have customers now that are interested in looking at this and using this for some of their applications, where we can immediately plug this FPGA card into a system and we can expand the memory available to those servers. So the FPGA is the beginning part of our journey, right, as we start to put more and more functionality into our devices. But eventually, we're building a system on a chip, an SoC. And by the way, this SoC just happens to have a 256-lane switch attached to it, right? So, I always tell our team, there's a lot of people that are building switches, right? And switches are needed in various forms, whether it's switches that are done through repeaters or switches that are done through, standard logic and various kinds of ways to do things. But what we're building is a smart SoC, right? Some intelligence into the device that will allow us to make, some of these system level optimizations, right, that you won't see through a vanilla switch. And it will allow us to be able to manage the devices that are connected to our switch. to be able to provide better efficiency at the system level. And this is the chip that we're designing that will be able to demonstrate in the next year. So just an example of other kinds of improvements that we can get, right? We talked about the swapping, but also now as from a chip standpoint, we can connect, compute, memory, storage, networking, onto our SSOC, and then with that be able to, have less amount of hops to memory, right? Instead of having to go all the way into the CPU memory, now we can have devices accessing a shared pool of memory attached to us, right? We've talked about the swap space already. Instead of swapping to SSDs, we can swap to pooled set of memory as well. So eventually, with all of this connected and with the chip connected, right, we're looking at having additional memory on the order of, several tens of, if not hundreds of terabytes, right, connected to us, and then have that pool of memory be a NUMA hop away, right? And that's the targets that we're going after on the latency side. And we believe by doing that, we'll be able to greatly enhance the overall system performance that people are constructing today. So again, as we start to look at OCP and what OCP is doing in conjunction with the work that we're doing with the CXL consortium, right, we see an intersection of a lot of things and a lot of functionality that we're going to be able to provide, right, into these solutions, right? One of them I talked about is the distributed control of resources, right? As you have these mesh networks connected through CXL, and our chips will connect to each other as well, and so you can create various kinds of topologies depending upon what your system requirements are. But then we have the intelligence within each of those switches to be able to control the devices to which they are attached, right? And so that will allow, even just from a visibility standpoint, if you try to, one of the things we tried to do was look at the traffic through a server operating in the data center. It's very, very difficult to characterize all of that because of the sort of the closed nature of what these look like, right? Eventually, what we'd like to do is we have these devices connected to our switch. We have to count the packets anyway, just to make sure that they're going in and out as they should, right? And by counting all those packets, then we can tell you exactly where your traffic is going, right? This is what we did early days of Ethernet. Just having that visibility, led to QoS and led to better architectures because we had that visibility, right? And having the connectivity and the intelligence in our SSOC to do that is going to enable better ways of designing these architectures, right? The pooled resources, as we've all talked about, not just memory, but compute and storage as well, right? And we're working with all of the companies associated with creating those in order to create these pooled resource environments, right? Flexible architectures to be able to move things around, dynamic allocation, right? These are all things that are going to become a reality, right? We've been talking, at least I've been talking about these kinds of architectures since back in my days at Xerox and Xerox PARC, right, in terms of creating these devices. And now we're starting to see this as a reality and something that we're going to start to demonstrate more and more of as we get more of this running in the lab. So you have at least my commitment that you will never see me on stage talking about something that I don't have already working, right? We have these elements running in the lab, and we'll start to roll these out as time goes along. But the end goal for us really is optimized efficiency at the system level, right? To ensure that we're getting not only the performance, but also the cost benefits of having these pooled resources. So from a OCP standpoint, if you look at our SSOC, ultimately where it can sit, there's a lot of flexibility, right? We can sit on the interface board, host interface board, and be able to fan out to a number of different devices, right? We can sit on the baseboard, right? And to be able to connect all the OAMs to that. Or we can sit on the OAM where we're actually controlling those devices that are on the OAM and connecting that into the baseboards and HIB. So there's a full, range of capabilities of what we have and the intelligence inside the chip to have the controllability of those devices as we start looking at these modular architectures. And we've got partners that we're working with now that are looking to see how we implement these kinds of solutions, given the capabilities of what we're building into our chip. So there's a lot of synergy, right, between what we are doing, the work that we're doing with the CXL consortium, and the goals of what we're looking here to do at OCP with the modularity of these designs. And our objective is not just to enable the connectivity of these things, but to have better performance, better ability to control these devices, right, as we start looking at these more and more complex architectures. So to conclude, right, the CXL protocol, right, combine that with the OCP vision and the standards that are being created is going to provide us this new level of hardware and interconnect composability, right? And this will drive the cost down and give us better system utilization as well as performance. And as we've shown, CXL is more about just connecting devices. It's about how you connect those devices, how you manage those devices, how you do it in a distributed fashion, how you control things from the kernel all the way up to the Kubernetes management of workloads, right? There's a talk earlier where they talked about those various levels along the stack that need to get controlled, right? So you've got to be able to have controllability of the hardware so that it matches well with what your system level software solutions need to be, and we're building that capability in to be able to have that controllability. And these advantages that you're going to get above just the connectivity alone is what's going to create these orders of magnitude difference in performance. And we'll start to reveal more and more of that as we go along. Resource sharing is going to be second nature, right? With memory and accelerators and everything that's coming up is going to be enabled by what we are doing. And then finally, again, with the extra added things that we're putting into our chip to help things at the system level will, again, enhance things even more. So we're not talking yet about, all of the system level features that we're building into our SoC publicly, but under NDA, we are having these detailed discussions with the entire ecosystem and really understanding how we raise the bar in terms of connecting CXL devices and to be able to use them as efficiently and as performant as possible. Okay, that's my talk today. Any questions?
Hello, my name is Wei Feng. I'm the tech chair for OCP AI hardware software code design work group. And we are looking to polymorphic architecture for future AI applications, which has a lot in common with what you mentioned, like a dynamic resource allocation, flexible architecture, and so on. So I'm just wondering, do you have like a simulation platform or even prototype for us to leverage?
So currently, we are working very closely with Intel, and Intel has been very, very good partners with us in supporting us in CXL consortium as well, and as in a number of other things that we're doing. So we do have servers and our FPGA platforms in there where we can do some of this work that you talked about in real time, right? We are still adding more functionality right into that system, but we're also designing our ASIC as we go along. So we've got things in simulation, all that. So we're in very varying stages, across the board of all this functionality, and I think it's just going to depend on the kinds of functionality that you'd like to do on that. But eventually, we want to have this platform in place that will provide most of the capabilities that we can of the chip, so that at least we can start to really characterize the value that we're going to get in situ, right, in the lab, and to be able to quantify it. So it is coming. Yeah.
Hey, great presentation. Thank you for coming today.
Thank you.
I had a question about the example that you showed where you had server A and server B, your FPGA connecting CXL to the host, memory within each FPGA. The interconnect between the two servers, is that still CXL in that interlink, or is you using Ethernet to be able to get to a larger scale in terms of the reach that you can get to as well?
So it is CXL protocol. And we will talk about the method and the details of how we're doing that as we work in conjunction with the CXL consortium. Our objective is ultimately to make that a part of the standard. But we believe that CXL is going to be valuable with the PCI, as we know of PCI Express, right, inside the box and inside the rack. Once you go outside of the rack, try to go rack to rack, especially if you're going to do PCIe Gen 6, now you're going to get a little bit of challenges of doing that. In addition, we've seen many companies in the PCI Express land tried to do all of this in PCI Express cabling, right, in the rack. That has proved to be a very significant problem. The connectors are brittle, the cables don't bend very well. I mean, there's a lot of issues associated with that from just a data center management standpoint. So we're looking at other ways, right, that we can take advantage of the lower latency protocol of CXL while at the same time being able to do the reach. And so, we believe that CXL and Ethernet are going to coexist for years to come, and we're trying to figure out how can we leverage all of this. Okay, I think that's it for today. Thank you very much.